Good afternoon, everyone. Welcome to our webinar today. My name is Jan Thomas. I am a training program manager with the Washington Center for Technical Development, or CTD, and I'm pleased to be here today to support today's webinar with our presenters. The Center for Technical Development exists to provide technical training and professional development opportunities for conservation district staff and partners in Washington, as well as to help facilitate sharing and networking. So a big thank you to Danny for reaching out today to the CTD for this programming. And just to plug that if you have relevant training ideas, projects, programs to share, please do reach out to us because we would love to hear from you and help coordinate. Just a couple of quick Zoom logistics for you today. We are in a webinar format, so you won't find access to the usual chat or raise hand features that you might be used to in a meeting format. But instead, we're going to ask that you put your questions in the Q&A box. So that's a kind of a rectangular call-out box with a question mark inside. That's going to be how you're going to ask your questions, and Danny will be moderating that. Also, this webinar is being recorded, and you will find the YouTube link shared out through the Washington Soil Health Initiative blog and on our CTD website in the coming days. And I'm going to pop a couple of things in the chat just for CTD contacts. If you are interested in our website or contacting us, and I'm going to just turn it over to Danny, who's going to kick us off today.
Thanks so much, Jan. Hi, everyone. Welcome to our second annual Making Soils Data Actionable webinar series. I'm Danny, the Senior Soil Scientist at the Washington State Department of Agriculture, and I am so excited to welcome you all today to talk yet again about soils data. All month long, the Washington Soil Health Initiative is showcasing projects across Washington that use soils data to make real-world on-farm decisions. And we're doing this because we love soils, but also because we know that soils data can be really confusing. More soils tests and data are available to farmers than ever. And while it can be empowering, new information can also be difficult to translate into action. Today, you are here to learn about soil compaction. A quick announcement, however, is that next week at the same time, we'll be talking about precision agricultural technology and data, and the following week about nitrogen credits and fertilizer budgets. So let's move on to why you're here today. We have Haly, Neely, and Natalie Sturm to demystify soil physical properties, specifically how to measure and manage soil compaction. Haly Neely is an assistant professor of applied soil physics in the Department of Crop and Soil Sciences at Washington State University. Her research focuses on soil physical health, particularly soil compaction and its impact on crop productivity. Natalie Sturm is a PhD candidate at WSU with a bachelor's degree from Montana State University and a master's degree from South Dakota State University. For everyone in the audience, as Jan said, there will be a Q&A at the end, so feel free to post your questions as we go. And otherwise, thanks everyone for being here today. Haly and Natalie, feel free to take it away.
Great, thanks, Danny. And I'm so excited to be here to talk about soils data with everybody today. Share my screen and get the presentation going. All right, so like Danny said, we're going to be talking about soil compaction today, kind of all aspects of it. So I'm going to talk about kind of what soil compaction is, kind of some definitions. I'm going to talk about kind of how you get some of the data and quantify measuring soil compaction, and then kind of what some of those thresholds are going to be. I'm going to pass it over to Natalie to talk about the management practices for soil compaction, because that's really at the heart of her PhD research, and I'm going to let her present her own research on those topics. So first off, what is soil compaction? So it's kind of got a little bit of a nebulous definition. So really, it's a decrease in soil porosity. So if you look at kind of a typical soil, get a laser pointer, kind of our ideal soil would be about 50% solid, so our minerals, organic matter, sand, silt, clay, or textures, and then 50% water and air, so that our pore spaces, they can be filled with water or air. And as your soil becomes compacted, that porosity is decreased, so you can hold on to less water, and then you have an increase in your solid fraction of your soil. It also can change the the aggregation or the structure of your soil. So this picture here on the right, you can see kind of a nicely structured soil, lots of pores and lots of cracks for roots to go down in, for water to infiltrate into the soil. And then on the left here, this is a compacted soil bed. And you can kind of see the structure almost looks like dinner plates stacked up on top of each other. And it's very difficult for roots to move through that soil, not only because of the lack of pore space, but also because that structure is really difficult for roots and water to move through, because kind of that stacked structure of the soil. We know this is a serious environmental problem. There's been research done on this since before even the 50s, but those are kind of when the first peer-reviewed studies started to come out. So it's something we've been dealing with for a very long time. We can have surface compaction, so you kind of see the wheel tracks here on the left versus kind of the non-compacted part on the right. We can have subsoil compaction, reaching down to more than 3 feet in the soil sometimes, where you get these compacted layers that are way down in your soil. And even though this is more of a physical soil property, we think about it, it actually impacts all of soil health. So if you have a lot of compaction, you can get really anoxic conditions, you can get nitrogen losses from that, you can get differences in your microbial communities, different bacteria or fungi. So because you're impacting the physical space of the soil, you kind of impact all of soil health. You can have problems with crop emergence, restricted rooting, reduced nutrient uptakes, reduced yield, and then runoff, flooding, and erosion also due to compaction. Kind of just a visual about what kind of this physically looks like. So more compaction, you tend to get shallow roots. So you kind of see this here, this little cotton plant when I used to work on this down in Texas. You're supposed to have a nice taproot, like this one here on the right, but it hit this compacted layer and just kind of went off to the sides, call that a J root or a hook root. Less water and infiltration, you can see that kind of here. Less plant available water, lower porosity. Again, you can kind of see some problems with crusting and emergence. This poor little cotton seedling kind of grew up, hit that crusted compacted layer, and then grew right back down and did not emerge. So this is kind of what it visually looks like when you have more compaction versus less compaction in your production fields. So here's kind of how it happens. So here's a water truck that we were using to purposely compact the soil, which Natalie will tell you about. I would never do this in a production field. This was done on a research farm. So as those tires are driving across the soil, it starts to compress in the topsoil due to that contact pressure. But then as the axle load increases, the weight on that axle increases, then it actually will transfer that energy through the soil profile. And that's where you get those deeply compacted layers 2-3 feet down from the soil surface, especially if the soil is kind of more wet. And then Natalie will talk about kind of how that happens, where the energy just gets transferred from the surface all the way into the subsurface. And equipment just keeps getting larger. So we're actually seeing more and more problems with compaction in recent years than we actually ever have before. This is from a nice review paper that was looking at compaction and wheel load increases. I believe this was done more in Europe, but you can see year over year, our wheel loads just keep increasing. Our machinery just keeps getting larger and larger and larger. One of Natalie's favorite papers cites that the equipment now is the size of very large dinosaurs. Cephalopods, is that correct, Natalie?
Sauropods. Our heaviest equipment is the same or increasing weight as sauropods.
Thank you. I'm not a paleontologist, but Natalie loves that fact. So the equipment is getting very, very large. So this heavy machinery is causing compaction. Also, different tire configurations and inflation can cause this. Driving on soils that have moderate water contents can also make things worse. Natalie will talk about that. Very wet soil, you can also get more shear stress and molding of the surface. And then you can also get plow pans from tillage as well. I love this image down here on the bottom. This was done a couple decades ago in the Midwest, where they excavated out a bunch of soil and then layered up soil and lime and then drove over the top of it so you can see the wheel depressions and you can see how far that compaction can go down into the soil. This was a study, they were testing different inflation pressures, I believe, in those tires. And then just the table there just kind of showing some of the axle loads for equipment that we use all the time, different grain carts, slurry tanks, tractors, and just the mass of this equipment is just causing more and more compaction issues. All right, so now we're going to talk a little bit about getting data, so how we kind of measure soil compaction. So first, just some kind of visual indicators like we were talking about is kind of the first step when we're looking at soil compaction. Like, does it just look like it's going to be a problem? So ponded water is a big indicator that you probably have some compaction. For example, this is a red raspberry field in Western Washington, and these rows are heavily compacted, and the water just ponds and sits there for a really long time. The water's not able to infiltrate into there. Stunted plants. You can see this little corn plant on the left that's under a compacted wheel row. You can see its shallower roots, just a smaller plant overall. Often you can see a lack of emergence. So this is really common to see in like field entrances. I was not able to find a picture of that, but you can kind of see a spottier emergence in an entrance. It's probably due to compaction. And then our J roots or our hook roots, also another big indicator that we might have a compaction issue in that location. Quantifying it, another couple ways are kind of a little bit ancillary. So penetrometers are really common, these hand-driven penetrometers. We have kind of the single mass dynamic one. You can even have a little pocket penetrometer. These dynamic cone ones are probably the most common. These are great to just get a little snapshot because you just push them into the soil, and the more force it takes to push them into the soil, the more compacted the soil is. Moisture, though, makes a big difference when we're using one of these. Who's using it? So someone taller than me versus someone short like myself are going to have very different forces with that. The texture makes a big difference. So for just getting a snapshot or just kind of getting an idea, they're great, but they're not very repeatable. Downforce maps, if you happen to have a hydraulic downforce on your planter or drill, that can be a good indicator of that. You can kind of see some areas where it's picking up that, it's applying more downforce in those spots in the field. That can kind of maybe give you a tip that maybe something's going on. And then there's a lot of remote sensing tools that are available now. This is a little map of NDVI for a field in Whitman County. NDVI is Normalized Difference Vegetation Index. It's just a measurement of greenness, basically. And you can kind of see this later on in a growing season, especially in dryland situations, that certain areas of your field might be drying out faster than others. And that might be an indication that you have compaction in those areas. But kind of our gold standard when we're talking about compaction is bulk density. So this is our dry weight of soil per unit volume. So in this case, we have a lower bulk density here and then higher bulk density. So more weight for that volume. Remember, decreasing that porosity. A couple of ways we can go about doing this. We can take a soil core here with like a hydraulic core. This is my preferred way to do this. Much easier to get that, and you can also get more subsurface measurements. Another way that's even more precise but much more difficult is using one of these slide hammers. So you attach the slide hammer threads here to our sampler, pound this into the ground, dig it up, cut your volume, and then you know what the volume is for that. You can imagine it's very difficult to get these. It's harder to get subsurface measurements using this kind of sampler, but this is kind of the gold standard for how to do that. So you get your little soil sample. We have our known volume of soil. You're going to weigh that to get your field moist mass. It's not necessary, but it's kind of helpful to have that. Oven dry your soil for a couple days, 2-3 days, weigh it again dried, and then you take your dry weight and divide it by your sample volume, and then you have your bulk density. Another way we do this is penetration resistance, which is that force per area. It can be in pounds per square inch or megapascals, or there's lots and lots of different measurements, to do this. And the way that we do this in the lab, and I'm sure Natalie will talk about this as well, is using a hydraulic penetrometer. This is a lot more repeatable than a handheld penetrometer, but you do have to put it on the back of a truck. We have the truck actually chained to the ground, so nothing is moving at all. And then we drive this cone down into the soil and then have sensors on there measuring the depth and then the force it takes to drive this into the ground. So we get a nice profile with this method. Nice thing about this method is instead of getting one measurement for a given volume or depth of soil, we can actually kind of get a continuous measurement of force. So in this one, I have, unfortunately, depth in centimeters. We have force in kilograms, so more compacted versus less compacted, and then we can see our whole soil profile. So in this particular soil, we have a little bit of a plow pan or a little bit of surface compaction going on here, and then it decreases and then it picks back up in the subsoil. So we get a nice kind of profile of this. This is also a little bit closer to what a plant might see versus bulk density. So that's another reason why we kind of like this measurement of a penetration resistance over bulk density. So now we have visually identified places in the field where we think there might be a problem. We've gone out there with our samplers or our penetrometers, and we've kind of got some data. So we have some numbers of bulk density, we have some numbers of penetration resistance. So now what do we do with those? So for example, if we have a bulk density of 1.65 grams per cubic centimeter, very common units for bulk density, is that good? Is that bad? So NRCS would say, and it's true, that it depends on what your soil texture class is. So kind of an ideal bulk density is going to depend on if you have a lot of sandy soils, if you have more clay in your soils, and it can vary quite a bit. So take our example of 1.65. If we have a sandy loam or a loam soil, very common this side of the state, that's may or may not be a problem. Root growth might be impacted around 1.65, and it's going to be restricted definitely above 1.8, so we might be kind of okay. Silty clay loam, going to be a little bit more sensitive, so in this case, a 1.65 is going to be considered root growth restricting according to these guidelines. So your texture class, what your measurements of sandstone and clay are really going to impact what that critical bulk density value is going to be. Penetration resistance is even more convoluted, so there's really not very clear thresholds. Those measurements can be dependent on soil moisture, especially if you're using a hand-driven one, the texture, and also the crops. So crops have different sensitivities to different bulk densities and penetration resistance. One common value that's kind of thrown around is 2.5 megapascals, but some crops can grow well at higher penetration resistances than that. In fact, I pulled this table. I know there's a lot going on in this table, but one of my other graduate students kind of pulled a lot of all the literature she could find on different parameters and then the crops and then kind of what those thresholds were going to be. So if we look here for bulk densities, all these different studies, we're looking at bulk densities, and we have thresholds anywhere from 1.4 to above 1.75 for cereals and soybeans and cotton. All land uses might be 0.7 to 1.2 if it's a different kind of soil that's a little bit more sensitive to that. So the threshold can vary quite a bit with texture. Penetration resistance even has a wider range for different texture classes as well, between 0.9 and all of different megapascals. So it's that range again is quite large. So the point is that the texture class and then the crop you're growing also make a big difference on if you are at a critical measurement or not. And then I'll end with kind of an economic threshold as well. I did find this nice publication. It's not from Washington State, but this is from North Dakota and Minnesota. This was done in 2020, 2021. So they were looking at compaction that could happen during the 2019 harvest, and they estimated that the would be an economic cost of $587 million for every 10% of acres affected by deep wheel traffic compaction. And they got that figure by using the 3-year average for the prices for corn and soybeans, which is the red line here, and then taking the acres affected, the 10%, and then adding those two values together. And they estimated this was be due to yield loss and the expense of leveling the ruts. So compaction can really impact yield. We don't always have a good handle on exactly how much due to the different ways that crops are impacted by soil compaction, but the economic impact could be quite large of soil compaction. And with that, I'm going to switch this over to Natalie, who will share kind of what some things we can do, or some things we can do about this.
Great, thanks, Haly. I will share my screen now. So as Haly mentioned, in my PhD work, I'm primarily looking at how do we manage compaction if that's something we decide that we would want to do? And so I get the question a lot is, what is the best way to manage soil compaction? And unfortunately, the answer is you have to just try to avoid having it in the first place. Once compaction is present in a field, it can be really difficult to get rid of. And so I tell growers, if you're worried about compaction, the best thing you can do is try to avoid causing any more than you might already have. One of the top ways to do this is to try to delay any field operations until conditions are optimal. Of course, there's a big caveat to this. Sometimes we have to get in the field when we have to get in the field. We've got a window, we've got to go plant or spray or harvest. So, within reason, just kind of trying to keep in mind making sure that that soil is not too moist. And so again, Haly kind of mentioned this, but just to reiterate, soil is most compactable when it's in kind of that middle moisture content, right at the perfect time when, be great for germination and emergence. That's also when our soil is most compactable. So that's why, typically we say if you can hold off on planting a day or two, if you're really worried about compaction, that can be really helpful for managing and avoiding compaction. Another strategy for avoiding creating soil compaction is a system called controlled traffic farming. So in this system, all equipment passes occur on the same predefined lanes in the field. And so the rest of the field is untouched by a tire or a track from any equipment that you might be using. This system is really popular in Australia and parts of Europe, not as widely used in the US yet. There's a couple constraints to controlled traffic farming. The number one being all of your equipment has to be compatible widths so that you can maintain those specific driving lanes. And then the other thing is just the need for, GPS or tram lines, and that technology is not always accessible to everyone. For example, the use of controlled traffic farming is not particularly widespread in Eastern Washington, where I'm doing my work. A big reason for this is the topography. So we just haven't really yet figured out how to do controlled traffic farming in terms of the GPS requirements for that. And so, because we can't really use or aren't using controlled traffic farming too much yet here in Eastern Washington, growers ask, well, what about some other methods? So another really common method to manage soil compaction is to try to mechanically sort of rip or loosen up a compacted soil layer. These are two examples here of some different deep tillage implements. So on the left, there's a small plot size version of a paratill tillage implement, and on the right, we've got an ecolotill. So both of these implements, essentially the goal is you just throw them as deep as you can into the ground and try to lift or break up those deeper compacted zones. So there's a few potential problems with deep tillage as a compaction management strategy. The first is economics and price. So depending on the price of diesel, this can be a very costly practice. It can take a lot of diesel and a lot of power to pull these big heavy implements across the field when they're going that deep in the ground. So that's kind of the primary constraint there. The time spent in the cab is something else to think about as well, that the time and labor that this can take. And then, of course, as a lot of us are probably aware, and maybe you've heard of in some of the other soil health webinars, we can have a lot of unintended, consequences of tillage in terms of soil health. Particularly in the case of soil erosion, we know that tillage can be really problematic for that. And this deep tillage may also negatively impact your soil structure. And then in terms of, sort of how long is this result, a positive result from tillage going to last, we're not really sure. So it can be really effective to deep rip and kind of loosen up a deeper soil layer. But some studies have shown that after a few years, that layer has to be retilled because it has become compacted after, we've driven over it for a few more growing seasons. And so then we have to repeat the process. So there's some questions about how long lasting the effective tillage could be. So what are some additional alternative methods for managing compaction? I've put question marks by these because these are all very much still kind of being addressed and we don't have great answers to, but it's things that I'm curious about and that growers are also curious about. So, what about cover crops? That could be potentially helpful. I'm just kind of trying to increase overall soil health. Some people ask, well, what about, like a tillage radish or something like that? Again, kind of mixed results there. Sometimes they're able to sort of bust through a compacted layer. Oftentimes I see a tillage radish just kind of popping out of the ground. That's a great indicator of where the compaction is, but probably not really, fixing anything. Similarly, I often get asked about what about canola or sunflower and those types of tap-rooted crops. And so I'll mention a study that I'm doing to try to look at that and see how effective those might be. And then finally, a little bit more of an extreme measure, but could be effective is to just establish some perennials in really problematic zones. So whether that's maybe a hilltop or a field entrance, and just kind of manage that area in a perennial, just kind of either try to let it, sort of heal in that zone with the deep perennial roots, and then bring it back into production. So that's another area that we're working on and kind of interested in. Amendments such as lime and compost are often asked about. And so a lot of growers say, it'd be really nice if we could just have something that we can spray on there and have it fix our compaction. And so we're looking at some of those things. I unfortunately don't have a great answer yet on what amendments might help compaction, but something that we're definitely thinking about. And finally, spraying with drones. This is certainly an emerging technology that's probably only going to get more and more common. And this drone spraying kind of goes back to the original idea of the best way to manage compaction is to avoid causing it. And so with the drone spraying, then we have zero footprint on the field when we're spraying. Of course, that technology is still being developed and there's, economically not always viable for most folks, but something that I'm pretty interested in and, something to kind of keep an eye on going forward. And then just kind of stepping back and thinking very generally about managing our soil systems. So maybe we don't have a good answer for what to do to manage compaction specifically. I would like to say that, well, if we can't, specifically target compaction, let's just think about supporting crop and soil health in general. Basically providing the best possible environment for plants, even if compaction is present. I really like this picture. It's from one of my trials from a field entrance, a really heavily compacted field entrance. And hopefully you can see, I'm going to get the pointer too so you can see. See, we've got these wormholes and various root channels. And so even though this soil is just this massive compacted block, we do see that there is porosity for those roots to be able to grow through. So if we're kind of maintaining as good of a structure as we can, even in a compacted scenario, that might be able to help us better support our crops. So I'm going to talk just a little bit about some of the work that we're doing in our lab. And the first thing that we can talk more about in the Q&A, if you'd like, is really this need to be able to identify compaction at the field scale. And so, that bulk density method with that, slammer hammer tool that Haly was talking about, super precise and can be useful for us as researchers, but as a farmer, I'm not going to go out and sample my whole field like that. And so we're working on some ways to try to better and sort of more easily identify compaction across the field. And then what I'll address here is looking at investigating the actual effectiveness of some different management practices, specifically in the context of Eastern Washington, where I'm doing this work. So the first trial I want to talk to you about is evaluating a one-time compost application with and without deep tillage as a potential way to manage soil compaction. And this is occurring in collaboration with 2 farmers here in Eastern Washington. So the application rate for compost was extremely high. So we chose about 50 US tons per acre, or about 300 kilograms of compost per plot. The idea here is that you would never apply this rate across your whole field. You would identify a couple locations that you're really concerned about and see if that compost would help compaction and or the crop growth. And then in addition, we did deep ripping with that paratill to about 20 inches. I've just kind of given an example here of what the trial looks like. So the pink is where we applied compost, and then the lines are where we did tillage. And then in each field that we have in this study, I've got 2 locations. So an entrance, which is almost always compacted, and then either a hill knob or a hill slope. So I just want to share, if these will play. Oh, they might not play. That's okay. Just wanted to share some fun videos and images of a huge compost delivery, and then we calibrated our small little spreader here, and then I don't know if I'm gonna get my video to run, but that's okay. It was just a video of us applying the compost on a hill knob. And we even had to do it at night one time to get in before the snow came. So that was exciting. And then again, here's that paratill implement, kind of a small plot size one. And then the pictures on the right are what it ended up looking like when we were done applying the treatments. Oh, that one plays. So just to give you a little bit of preliminary information about what we found 1 year after doing these treatments. So let me orient you to what's going on in this graph here. So this is from our higher precipitation site. These graphs are looking at that penetration resistance, or how hard or easy it is for something to go through the soil, whether that's the penetrometer in this case, but that kind of relates to roots as well. So on the sort of the bottom or x-axis, we have that penetration resistance. So the farther to the right that you go, the more compacted or the harder it is to press into the soil. And then on the vertical or y-axis, we have depth. And I've just indicated here where that tillage zone is. This is about 20 inches. So that was kind of where the bottom of our paratill went. Each panel is a different treatment. So we've got ripping and compost, ripping with no compost, no ripping, but with compost, and then our control of doing nothing. And so what we've found is that the deep tillage was able to reduce that penetration resistance value. And so we kind of alleviated a little bit of that compaction in those zones, both at the field entrance and at the knob. The compost on the surface, kind of as we expected, didn't really do anything for penetration resistance. We didn't incorporate the compost, it was just applied over the top. Now, when we think about yield, kind of, the bottom line here, this is barley biomass. The reason that we're doing this in biomass is there was a bit of a fertilizer mishap, and so we essentially made forage barley instead of barley for grain at this site, but that's okay. We can still look at differences there. And so what I want to highlight first is the difference between ripping, which is on the right-hand side of both of these graphs, and not ripping. And there was little to no significant difference in the barley biomass yield due to that deep ripping. Even though we saw that difference in penetration resistance, it didn't ultimately translate to a difference in biomass. In the ripping plus compost treatment on the hill knob, we did see a significant increase in barley biomass compared to all the other treatments. Now at our slightly drier precip site, this graph is set up exactly the same way, where as we go to the right, we're more compacted, and going to the left is a little less compacted. Whoops, there should be arrows there. But again, just want to highlight that ripping treatment really did reduce the penetration resistance, kind of help to alleviate that compaction. There it is. At this site, we had spring wheat. So this is spring wheat yield and just in bushels per acre by the various treatments. Again, just want to highlight there was only a couple bushel increase at most in spring wheat yield due to that deep ripping, even though we saw a significant decrease in penetration resistance. At this site, compost really did help to increase the yield as well. But just remember that that didn't actually really do much, at least in terms of penetration resistance. So the compost really is that driving the yield increase is probably more due to that increase in nutrients, from the compost. As I mentioned earlier, controlled traffic farming is not particularly relevant in Eastern Washington right now. So growers are always asking me, what about crops? What crops can I use to try to improve my compacted soils? So to address that question, I created an additional trial, not on farmers' fields, because as Haly mentioned, not going to ask somebody to wreck some of their production operation just for me. But we imposed compaction on purpose to some experimental plots so that we end up with a compacted and not compacted treatments, so that we can look exactly at this question of, can different crop sequences help to improve compaction? So just to highlight the sequences that we're looking at, I've got a business as usual, very typical for Eastern Washington. The alternative replaces that first year crop with a sunflower. This is a crop I often get asked about. And then finally, we're looking at a perennial sequence to see, okay, maybe if we can take it out of production for a few years, will that give us enough of a boost or an improvement in compaction that could actually be worth it? So this project is definitely still ongoing, but I do have some early results from the first couple of years. First, just visually to highlight the difference in the fescue, the forage fescue. In the background here, we see white a bit taller, and then here in the foreground, a little shorter, definitely drier, having some issues with water uptake. So the compaction is having variable impact on crop yield. It was not a good year for spring wheat in that first year, but we did see that the compaction decreased spring wheat yield a little bit compared to the not compacted. There was no difference in canola yield across the sequences or the compaction treatments, and same for the fescue forage yield. What was pretty interesting, though, was that we saw a significant increase in spring wheat grain protein content. And this is kind of a negative result in Eastern Washington, where we typically grow wheat that is lower protein content. And so that's kind of a concerning finding that, we're hoping to look more into. So just to kind of summarize and wrap up, say, I'm interested in soil compaction. I'm either just curious about it or really concerned and need to start doing something. What are some ways that you can begin observing and experimenting on your own farm or farms that you work with if you're a crop consultant? So first is to identify soil compaction and what impacts is it having. So this can be in lots of different ways, as Haly mentioned. So those measurements of bulk density or penetration resistance, or just using other visual indicators. What can be really helpful is to take soil and yield data, whether that's direct measurements or observations, in the same locations over more than 1 year. The weather can have a really big impact on what a crop, how a crop responds to compaction. So in a drier year, you might see more impacts versus a wetter year, or vice versa, depending on where you are in the state. So having that repeated measurements can be really helpful in identifying what's going on. In the meantime, as I mentioned at the beginning, you can manage compaction by trying to avoid creating more compaction as much as possible. So we've identified compaction and some of its impacts. At that point, it's kind of up to a decision of deciding that do those impacts surpass your tolerance level, and that can have to do with your soil types, your cropping system, and kind of your economic risk, threshold. If you're curious about trying some management practices, I would suggest, pick a management practice, sort of start small. pick a tillage implement or a cover crop and pick a small area and try out one of those practices in that area. Maybe it is your field entrance or some other zone in your field that you're concerned about. What's really important is to leave a non-managed check. So if I wanted to paratill my entrance, I would suggest, maybe splitting that up into a couple different sections and only tilling half of those sections, leaving a non-tilled area, just so that you can compare to those results. And again, observing over multiple years is really important. We don't want just a one-time wonder. It's good to see what are the impacts of that management practice over many years, if possible. And with that, I think we're really excited to take some questions and discussion. And yeah, I just want to thank Danny and everybody at Washington Soil Health Initiative for letting us chat with everyone. I've got a couple QR codes up here that you can scan with your smartphone that'll link to a couple different things about compaction.
Thanks so much, Haly and Natalie. We are going to start with some of the questions that are currently in the chat, and for anyone else in the audience, please feel free to keep adding them into the Q&A box. So we have a question from Suzanne Bishop that asks about the kind of systems you guys have been studying. Natalie, your results are mostly for annual systems, but have you focused on perennials like tree fruit or apples or cherries?
No, it's
yeah, so go ahead, Haly. I was going to say that's a Haly question.
So I have done some work on this in red raspberries, because it's not so much the compaction is hurting the plants, but it's actually causing a delayed entry into the fields due to that ponded water. As far as perennial systems, like Natalie was talking about, they're already kind of are controlled trafficked, because you can only go between the perennial plants. And they're also often more spoon-fed their nutrients as well. So like in raspberries, you just put everything through the lines. So that we really don't do as much work or see as much of an impact of soil compaction in those more perennial tree fruit crops. It doesn't seem to be an issue. Now, I'm not saying that it's not an issue, but it doesn't seem to be as big of an issue as more production fields.
Thanks. And we also have a question from Curry Fleggy about compaction measurements. So how closely related are the different measurements? And can you estimate bulk density from, let's say, measurements like those from the penetrometers?
Yes. Yes, there are models that will predict bulk density from penetration resistance, and we do that in the lab some. There are some fudge factors that you need to apply to those. So actually one of my other students just finished up a paper. So she was able to predict bulk density reasonably well from penetration resistance, but it was field specific. So whatever model she chose was specific to that field. She could go back the next year to the same field and use the same model, but it was fairly field specific. So you can do it. There are dozens of models that you can use to do those predictions. And again, they're awfully specific, but you can do that. I mean, and obviously, higher bulk densities, you will get higher penetration resistance values. Like they are related, but it's not a true one-to-one.
That tees up another question really nicely, which, I'm sure as the compaction scientist, you get asked often, what number should my soil be at? What is the exact value to optimize crop production and soil health? What do you tell folks who ask about that?
Natalie?
I get to say it depends. Yeah, and unfortunately, it does depend quite a bit on your soil texture, as was highlighted a lot with the bulk density, and on the crop itself. Crops have pretty wide differences in tolerances for compaction. So, for example, wheat crops or other small grains tend to do pretty well in compacted scenarios compared to something like a canola or a cotton, throwing that back to Texas. And so it really does depend on your system. And so that table of bulk density thresholds, which is also one of these QR codes as well. That's kind of a good starting place for kind of gauging where you're at if you were to take bulk density measurements or have your crop advisor take those measurements. And so that's a good starting place. But I would say it's also important to measure or observe other factors as well. So is there a yield difference across your field due to bulk density? Maybe, but maybe not. And so it's good to have more than just bulk density or just penetration resistance to really find out if it's a problem or not.
I feel like we say it depends a lot in soil science.
Yeah.
So another question from Curry about equipment. Are there equipment upgrades you'd recommend that have a quick return on investment for decreased compaction? You showed the graphs of things getting heavier over time. What do you guys tell people about equipment?
Yeah, Haley, I can jump in really quick about that. So just one thing that I hear from growers is if you are using, if you've got tires on your equipment, so if you've got tractors, that's kind of a different thing we can talk about. But if you've got tires, one of the most effective things I've heard from some growers is really trying to reduce that tire inflation pressure as much as you can. There's some management that goes into that. You have to be able to still, pull your implements and have the traction and things like that, but really trying to reduce that inflation pressure. I've heard that there are some farmers trying to add like onboard air compressors essentially to inflate and deflate tires kind of on the go, so that maybe you're moving your tractor to a different field, you want a higher inflation pressure if you're on the road, and then reduce that inflation pressure once you get into the field. That's something that seems pretty promising, and that growers have told me is helpful. Again, that it's it's a cost, it's another equipment, a little piece that you have to add there, but that's something that could be helpful. So.
Okay, another question from Dean White. So we hear a lot in the soil health space that integrating livestock is one of the core soil health principles. And I'm wondering if you guys can talk about the potential risks of increased compaction from that practice.
Yeah, I might jump in on that because I actually do have another trial where we are integrating livestock, although when the soil is dry, because of this very reason. So yes, there can be adverse effects of livestock for sure. I know that Doug Collins, I believe, is also looking at livestock integration. I'm not sure where his results are. I think he's also looking at compaction in his trials as well. So it is definitely a problem that we know about, very well documented, and kind of like Natalie, just keeping the animals, from being really confined in one spot. We know that mob grazing can be helpful in certain circumstances where you kind of open up a small section of ground to them. They mob graze it, then you move them off. Moving your water troughs around, moving things around so they're not congregating in the same spot over long periods of time. And again, or just not letting them have access to the fields when it's too wet. So it is something that we are looking at and aware of. And usually livestock, though, they're also more usually surface compaction and not subsurface compaction. So even if you do get some, it is at least easier to manage compaction from livestock versus compaction from equipment, because they don't tend to compact the subsoil like a tractor does.
So the Washington Soil Health Initiative recently interviewed people about their soil health challenges, and we presented everyone with a list and asked people to say yes, no, or unsure. So do you have soil acidity? Yes, no, unsure. And the most common responses for compaction was unsure. Out of all of the soil health challenges, it's the one that growers seemed to not really know if that was an issue for them. And do you find this to be common when you're engaging growers? And if so, why do you think that is?
I'll let Natalie take that. Maybe you could talk a little bit about your focus groups that you ran as well, that kind of look at something similar.
Yeah, for sure. So that result definitely is very is confirmed by what we hear from growers. And so as part of my PhD work, I've done a series of focus groups with farmers specifically about soil compaction. And so I did several in Washington and then some in Texas and Wisconsin as well, just to try to get some different cropping systems and soil types. And across the board, that's kind of the main barrier, is the unknown. Do I have soil compaction? A lot of growers are like, yes, probably. But is it impacting the bottom line? How do I measure it? Yeah, we're seeing those questions. Yeah, all over, not just in Washington. And so there's definitely a big need, from us as scientists and even and crop advisors and conservation district folks to try to start measuring compaction a little bit more for growers when we're able to, and kind of help to better assess what's going on with compaction. So that's, I don't know, that to me, that's kind of the next step, is just trying to identify compaction, more and more, and yeah, see what's really going on.
Yeah, and even without taking, lots of measurements and bringing out the big fancy tools, just looking at your fields, and is there a place in your field that's like having trouble draining? Is there a spot in your field that like emergence always is kind of poor? And then if you can kind of see those patterns, then maybe borrow a penetrometer or call me, I'll bring out my truck, and then we can kind of compare like that spot versus a spot that seems to be functioning really well and seems really healthy. And then we can identify like, oh yeah, I think this is actually driven by compaction, or no, it's a different issue. But that's kind of that first step, is just looking at kind of the differences in yield and plant productivity across your fields, and then we can go poke some holes and identify what we think might be going on and kind of diagnose that problem.
Yeah,
so,
and one, oh, good.
No, go ahead, please.
I was just going to say one thing that I don't know if we've said yet in this talk is, you're probably always going to have some level of compaction. That's just sort of the nature of, our large scale agriculture. We're probably always going to have some degree of compaction. And so, I don't want to be like alarmist or anything, like it's okay to have some compaction. It's that question of, when do you want to do something about that, all of us are trying to help answer.
That's really helpful. So one of the things your research seemed to suggest is that there are instances where tilling, or at least tilling plus compost, reduced compaction. Maybe I got that wrong, but I know that that's a pretty common idea, that when you have compaction, you can sort of till your way out of the issue. And maybe you guys can talk about when that does work and when that doesn't, and some of the trade-offs there.
Yeah, I can start just based on kind of what I've seen and previous research that I've come across. So tillage and what we found with those was that, yes, it can reduce those measurements of compaction. So we can lessen penetration resistance or reduce bulk density. So in terms of those measurements that we typically think of as, that's compaction, yes, we can improve those with tillage in some cases. However, the problem is, at least, so far in my work and then in other work in Washington and across the country, that doesn't always lead to a yield increase. So even though we're moving the needle on the compaction measurement, it's not really translating to anything significant in terms of the bottom line, that is producing a crop. And so, why that's the case, I'm not totally sure yet. And Haly can chime in a little bit more there, but that's kind of why I tend to say, some level of compaction is always going to occur. And if it's not affecting your yield to a point where you're worried about it, maybe that does not warrant the pass of the tillage implement. And you can hold off and save yourself the cost of diesel and save the potential, soil health negative effects from that. So yeah, Haly, I don't know if you have anything else to add.
Just the other thing that I would just add on to that is that the silty soils that we have in Eastern Washington are particularly susceptible to erosion.
Mm-hmm.
And when you look at the literature, like people have done these, extensive literature reviews, it's actually more of a negative to deep till than to do that, because of that, just that very, very real risk of wind and water erosion. Deep tillage tends to work the least well. and be the most risky on silty soils, which is what we have as well. And it doesn't totally surprise me that like the paratill doesn't solve all of our problems, because you're just doing kind of one pass and it's attempting to kind of shatter your soil, but you're not really getting it back to the pore size distribution that it was to begin with. So you're probably increasing some of your bigger macropores, but the pores that are within those units, within those structural units, are still compressed. So that soil is still probably not holding on to water and nutrients like a less compacted, more natural soil.
Well, we are at the end of our time today. Haly and Natalie, thank you so much for being here and sharing all this information for us. And thanks to the members of the audience as well for your time and attention. You will be able to find the recording on the Soil Health Initiative website shortly, as well as the Center for Technical Development's YouTube channel. And hopefully we will see you all next week to talk about precision agricultural data and technology. Thanks everyone so much.
Thanks, everyone.